In 1999, a consortium of industry and academia headed by PCI conducted the landmark press test to verify design methodologies for precast frame systems to withstand seismic forces. Now, a similar consortium headed by PCI is addressing methodologies to design floor systems or diaphragms to more effectively contribute to a structure's seismic performance with the Diaphragm Seismic Design Methodology, or DSDM project.
This particular project was first initiated about 4 years ago, and it was really a spin-off of an earlier project called PRESS that we initiated. The precast concrete structures industry has always been a leader in design and technology, and we've done that by conquering any barriers that we've encountered to using precast concrete building systems. And now we're going for the gold. It's not good enough that precast concrete is okay to use in a seismic zone. Okay, we want it to be the best system to use. And in fact, this demonstration and this whole project is really advancing us more in that direction.
It's not only for high seismic zone, it's going to be beneficial for the industry in all seismic zones.
The code requirements for seismic design are much more pervasive. Really across the majority of the United States, there have to be considerations of seismicity. Even in Texas, where I come from, that's a requirement. So that has forced us to develop answers for engineers on how to design structures and seismicity in areas they wouldn't even considered it before. Then also with the advancement of the industry, there's more needs required, more applications required, more interest required, so we have to satisfy this expanding need. And what we're testing here is the performance of these floors and roofs, actually how they perform in a seismic event. Little is known about this performance, so this program is one that both analytically and test out at the site here will determine code ways that you can now design properly the floor and roof to withstand seismic loads.
The project originated with PCI. PCI has acted kind of as the germ cell of the project and coordinator of the project. But to do a project of this magnitude, it's different than most of the other projects we've done, which PCI has pretty much managed itself through our Research and Development Committee. This one, because of its scale, we're over $2 million invested in this, and possibly going up to $2.5 million, required a lot of collaboration and participation. But it's not just for the money. It's also because the knowledge and specialty information that we needed, special equipment, special techniques, analytical tools, can only be gotten by reaching outside our immediate industry and involving people who have an interest and expertise in this area. So as a result, you're seeing a project here that's the culmination of a really wonderful collaboration. Not just money coming together, but people's minds and ideas coming together.
Also helping to bring minds and ideas together were the contributions of the Charles Pankow Foundation.
It was a real pleasure for the foundation on our very first year of grant making to learn that PCI and this project was proceeding on a path exactly as we intend our research contributions to do, so that something over $400,000 of the Charles Pankow Foundation grant is helping this DSDM project go forward. Its purposes to deliver final building codified results in innovative precast diaphragm construction are extremely well aligned with the purposes of the foundation.
As with the landmark press test, completing the collaboration are 3 preeminent American universities.
The way we decided to perform this project is have Lehigh do tests of existing reinforcing details that are used in the floors today to examine their performance, see if the performance was good and bad in terms of strength and stiffness and deformation capacity, which we call ductility, and also to characterize them so that we could actually take experimental data from Lehigh and build our computer models of floors. Then we did earthquake simulations of the structures with those models, and at the back end we want to validate our computer models that it's taken a number of years to build by making predictions of a structure like the structure behind me, and actually simulating an earthquake with the structure here at UCSD.
What we will do is subject this half-scale structure to progressively more severe earthquakes, and as an end result, after analyzing them, develop a design methodology that will eventually wind up in code.
That test will take place at one of the most unique facilities in North America.
Behind us, we have what we call the NEES UCSD shake table. NEES stands for Network of Earthquake Engine Simulation, and is located at UC San Diego. This is the largest shaking table in the United States. The table can hold 2,000 tons. The structure we have at the back here weighs of the order of 400 tons, so we can still place 5 times more weight than expected.
While testing the structure will calibrate and verify models, it will also serve another purpose. Robert Fleischman gives us an overall view of just what is being tested and why.
What we're testing in the structure is actually 3 different floor systems. That makes it a little bit unique. On the bottom floor, we have double T's that have a very thin topping slab on top with wire mesh. That's a cast-in-place topping slab. On the second floor, we have hollow core with the same cast-in-place topping slab. And on the third floor, we have just precast units, what we call a untopped or pre-topped system. And this is the concept of what we call a total precast system, a total precast solution where the entire structure is made out of precast elements. And so none of these systems right now are specified for an area like California. So really, I mean, what the design profession is doing right now is saying there hasn't been a project like this to show us how precast could be used. So each one of these systems, if we are able to demonstrate their good performance, will represent an advancement in their geographical area where they could be used. And so if we're able to specify a precast diaphragm that works in an untopped fashion, the ability to use a total precast solution in a high seismic area will be a reality.
It is time to start testing. As project partners from across the nation gather, the structure is prepped. Throughout the shake test phase, the seismic records will increase in severity, culminating in an event that might occur once in 2,500 years. The first test, though not as severe, might be as rare, as it is simulating the kind of ground motion that might occur in Knoxville, Tennessee.
5, 4, 3, 2, 1, ready.
The test is a success and the structure performs as expected. Next up is the Seattle Design Basis earthquake, a severe event that might happen once every 475 years.
PCI 3, 270%. 5, 4, 3, 2, 1, ready.
A visual comparison of the first 2 tests makes it clear that the seismic hazards faced by Seattle are more severe than those in Knoxville. After these 2 design-based tests, damage was as expected. Robert Fleischman previews his hopes for the upcoming tests.
Next week we'll be testing the Berkeley motions, both a design basis earthquake and a maximum considered earthquake. And if the structure and the floors can survive through those, we'll have successfully demonstrated those systems for those demands.
Due to the severity of the upcoming ground motions, the researchers implement extra safety measures.
Because of the extreme nature of this ground motion, we've added some precautionary measures. We've added 2 restraint towers on either side of the structure. The towers are there just as a precaution to protect the equipment down below, in particular the actuators underneath the table, and they're not touching the structure. They're actually set back 6.5 inches. We don't expect failure, but as a precautionary measure to protect the equipment here on the site, we've implemented safety measures.
Just prior to the day's testing, Jose Restrepo gives a preview of what to expect.
The structure is going to undergo 2 major input ground motions to earthquakes that simulate conditions in Berkeley. This is the highest seismic region of the country. And we are going to simulate this scenario with a record obtained during the 1989 Loma Prieta earthquake in San Francisco or nearby. And this has very high velocity pulses. In fact, has 5 pulses, 1, 2, 3, 4, 5. So the structure is going to be very severely shaken.
The team is ready to proceed into uncharted territory, the Berkeley design-based test, replicating forces experienced close to the Hayward Fault maybe once in 475 years.
PCI 6, 100%. 5, 4, 3, 2, 1, running.
It is time for the most extreme test ever conducted on such a massive concrete structure. The Berkeley Maximum Considered Earthquake, one we have little chance of experiencing, or so we hope.
PCI 8, 100%. 5, 4, 3, 2, 1, running.
In the end, all settles and the structure stands.
Success. We have to check everything close up, but it looked like it performed really well, so we're excited.
The test phase is complete, with the task of transforming the results into practice ahead. Robert Fleischman comments on how the structure's performance and the test's successes will make that possible.
The testing program at UCSD has successfully demonstrated that our models that we built based on the Lehigh tests have a high level of accuracy. We're really excited about that because what this allows us to do is have confidence in moving forward with parametric studies. We look at all different types of structures all over the country, different configurations, different designs on the computer, and we can say that we have confidence in it because we predicted this test and we ran the test, and the prediction and the response are right on top of each other. I'm also quite hopeful that with the strong team that we have, we can actually truly transform our research into practice and get this into the codes. The result of our work will save lives, will make the construction industry more competitive, will open up markets for precast concrete.
What you're seeing here is the seed crystal of a new dimension in design that's going to propagate over the years and basically overtake the previous ways of doing design work. That's really the value of something like this.